Are transistor DC biasing. For the transistor to be biased in its operating region, the following must be true: that the base emitter junction must be forward biased, and the resulting forward bias voltage must be equivalent to 0.7 volts. The base collector junction must be reverse biased, and this reverse bias voltage has any value within the maximum limits of the device. Remember that in the bipolar junction transistor operation region, we have the linear or active region where the base emitter junction are forward bias and the base collector junction reverse bias. And also we have the cutoff region. The base emitter junction and the base collector junction are reverse bias, and the saturation region where your base emitter junction and your base collector junction are forward bias. So we have this first configuration, the common emitter. Under common emitter, we have the fixed bias circuit. It is a straightforward and simple circuit. So we have an amplifier without an emitter resistance. So this is our input and this is our output. So this is what your amplifier circuits look like. Remember that during DC analysis, the capacitors are open. So we have only this circuit in DC analysis. So we have to determine the flow of your current. So we have IB, which is going to your transistor as well as IC. And we have IE going out from your transistor. So applying your KCL to determine your current equation, we have IE is equals to IB plus IC. And remember that the DC ratio, if it is a common emitter, it is called beta. It is output over your input. So we have a current output, which is IC, and your current input, which is your IB. So therefore, beta is equals to IC over IB. Solving for your IC, that is equivalent to beta IB. And applying this term of your IC, which is equivalent to beta IB, to your equation IE, so therefore IE is equals to IB plus beta IB, or IE is equals to the quantity beta plus 1 IB. So for the first analysis, we have to get the input side loop. So applying KVL in this circuit and looking for the voltage base, your voltage base is the voltage from this portion base with respect to ground. So we have VCC minus RB IB minus the voltage from your base to your emitter. We call that one as voltage base emitter junction, which is equivalent to 0.7 equals to 0. Solving for your IB, so therefore IB is equals to VCC minus your voltage base emitter junction over RB. And if we have to solve for your voltage at the base with respect to ground, we can have a VCC minus the voltage drop across RB, or it is equivalent to your voltage base emitter junction. And getting your IC, that is beta IB, and your IE is equivalent to beta plus 1 IB. Now at the output side, so that we can solve for your voltage at the collector terminal. So we have this one, BC, from your collector with respect to ground. And between your collector and your emitter, we call that one as your BCE, or your collector emitter junction voltage. So applying KVL again. So we have BCC minus RCIC minus BCE equals to 0. we know already the value of your IC in our previous slide. So therefore, we can solve for your BCE. That is equivalent to BCC minus RCIC. And solving for your BC is equivalent to your BCC minus the voltage drop across RC, or BC is equivalent to your BCE. So we have this example. So we have a beta of this transistor which is equivalent to 99. So during DC analysis, all these capacitance, your C1 and C2 is open. So we have to determine the following: IB, IC, IE, voltage at the base, voltage at your emitter, as well as the voltage at your collector. So we have to apply the current. We have the current IB, IC, and IE. Then for the voltage base with respect to ground, voltage at the collector from collector terminal going to the ground or with respect to ground, and voltage at your emitter is from emitter terminal with respect to ground. And we have a voltage collector emitter, which is from your collector to your emitter junction. So at the input side, we have 12 volts minus 240 k IB minus your voltage potential between your base emitter. And that is equivalent to 0.7. So we have IB equals to 12 minus 0.7 divided by 240 kilo ohms. So therefore, IB is equivalent to 47.08333 microampere. Solving for your IE, we know IE is equivalent to beta plus 1 IB. So we have 99 plus 1 times your IB. And that is your IE. And solving for your IC, which is equivalent to beta IB, therefore, we have IC is equivalent to 4.66125 milliamp. Then at the output side, we have 12 minus 2.2K IC minus BCE equals to 0. And solving for your BCE, that is equivalent to 12 minus 2.2K IC. We know already IC, which is equivalent to 4.66125 milliamps. So therefore, BCE is equals to 1.74525 volts. And BC is equals to your BCE. If we have to solve for your voltage at the base, that is equivalent to your voltage base emitter junction, which is equivalent to 0.7. And voltage at your emitter, since there are no resistor in your emitter, then it is equivalent to 0. Next, configuration bias is the emitter stabilized bias circuit. So this time, it contains an emitter resistor to improve the stability level of your amplifier. So we have your emitter resistor. We call that one as RA. So this is your input side, output side. During DC analysis, all capacitor are open circuits. So we have this circuit. We have IC going to your transistor as well as IB. Then we have IE going out from your transistor. So applying KCL, we have IE is equals to IB plus IC. Then your DC ratio, which is equivalent to beta, that is IC over IB, and IC is equals to beta IB. Applying that one to your IE equation, then we have IE is equals to IB plus beta IB, or IE is equals to beta plus 1 IB. So at the input side analysis, applying KVL to solve for our voltage base and voltage at the emitter. So we have BCC minus RBIB minus voltage base emitter minus RAIE. And remember that IE is equivalent to beta plus 1, and we have to substitute this IA to your equation. So therefore, we have BCC minus RBIB minus voltage base emitter minus RE times the quantity of beta plus 1 IB. Solving for IB, we have BCC minus voltage base emitter over RB plus RE times beta plus 1. And IC is equals to beta IB. Voltage base now is equivalent to your BCC minus the voltage drop across RB, or it is equivalent to your voltage base emitter junction plus your RE/IE. And for the voltage across your RE, which is also your voltage of your emitter with respect to ground, that is RE times IE. Then at the output side, so we have your BC, and the voltage between your collector to emitter is your BCE. Supplying KVL, so BCC minus RCIC minus BCE minus REIE. We know already what is IC as well as IE, so therefore we can solve for your BCE. So BCE is equals to BCC minus RCIC minus REIE. Solving for BC, that is BCC minus RCIC. And also, it can be a BCE plus your voltage at your emitter. So that is how to solve for your voltage of your collector with respect to ground. So example, we have this one. We have to determine IB, IC, IE, voltage at the base, voltage at the emitter, and voltage at the collector. So we have your voltage at the base. This one is your voltage at the collector with respect to ground. And we have a voltage of your emitter with respect to ground. Between your collector and emitter, we call that one as BCE. So at the input side analysis, we have 12 minus 240 KIB minus voltage base emitter minus 750 IE. Then we have to express IE in terms of IB, which is beta plus 1 IB. And solving for your IB, so IB is equals to 12 minus 0.7 over 240K plus 750 times your beta plus 1. So we have IB is equals to 35.78301587 microamp. And solving for your IE, which is beta plus 1 IB, so therefore IE is 3.58730157 milliamp. And for your IC, which is equivalent to beta IB, then IC is equals to 3.551428571 milliamp. Then at the output side, we have 12 minus 2.2 KIC minus BCE minus 750 IE. We have already the value of IC as well as IE, so therefore we can solve for your BCE. So BCE, that is your collector emitter junction voltage, we have 1.496380954 volts. And solving for your BC, that is collector with respect to ground, so we have BCE plus the voltage drop across your 750. And that is equivalent to 4.186857144 volts. And for the voltage with your base with respect to ground, so we have your voltage base emitter plus 750 IE, or that is equivalent to 3.390476619 volts. And for your voltage at your emitter is the same voltage across your 750. So we have 2.690476619 volts. Another bias is a voltage divider bias. So we have this input and this is our output. So during DC analysis, capacitor is open. So we have this remaining circuit. So we have IC going to your transistor, IB going to your transistor, and IE going out from your transistor. We have to get the KCL at the base terminal. So we have IE equals to IB plus IC. Remember the ratio if we have a common emitter, that is output over input, or that is equivalent to beta equivalent equals to IC over IB. Therefore, IC equals to beta IB and IE is equals to beta plus 1 IB. At the input side, this will be our circuit. So we have two branches of resistance going to your base terminal. So we have to apply this time your Thevenin's theorem. So at Thevenin's theorem, we have first step, which is we have to remove the load and replace with voltmeter. And solving for your BTH, that is equivalent to R2 over R1 plus R2 times your BCC. Step 2, we have to remove the voltmeter and replace 8 weight ohmmeter, and the BCC must be shorted. And solving for your RTH, that is R1 in parallel with R2, or that is R2 R1 over R1 plus R2. And the third step is we have to draw the Thevenin's equivalent circuit and putting back the load, which is your transistor as well as your RA. And your current flowing at your RTH is IB, and we have IE from your transistor going to the ground. So applying KVL, so we have BTH minus RTH IB minus voltage base emitter junction minus REIE equals to 0. Since IE is equals to beta plus 1 IB, then we have to solve for your IB. So we have BTH minus voltage base emitter over RTH plus RE times beta plus 1. Then for the voltage at your base, so that is from base terminal with respect to ground, it is equivalent to BTH minus RTH IB, or equivalent to voltage base emitter plus RE IE. At the output side, you have your BC, collector to emitter voltage, and we have your BE. So applying KVL, we have BCC minus RCIC minus BCE minus REIA. That is equivalent to 0. Since IC and IE have known already, so we can solve for your BCE. And for BC, that is equivalent to BCC minus RCIC, or that is equivalent to your BCE plus your voltage at your emitter. So what is the voltage of your emitter? That is equivalent to the voltage drop across RE. So we have RE times IE. So we have this example. So we have to determine the following: IB, IC, IE, voltage at the base, voltage at the emitter, and voltage at the collector. So during DC analysis, all of the capacitor are open. So we have now this circuit. So at the input side, using Thevenin's theorem, we have first to solve for your BTH, which is equivalent to 160K over 240K plus 160K times 12. So we have a BTH equivalent to 4.8 volts. Step 2, we have to remove the voltmeter and replace with ohmmeter. So we have RTH equals to 240K times 160K over 240K plus 160K, or that is equivalent to 240K in parallel with your 160K. So we have 96 kilo ohms. In step 3, we have to redraw your Thevenin's equivalent circuit. Then we have your IB flowing to your base of your transistor from your BTH, and we have IE from your transistor going to the ground. So applying KVL, so we have 4.8 minus 96 KIB minus voltage base emitter minus 750 IE. Then we have to express IE in terms of IB, where IA is equals to beta plus 1 IB. Beta is 99 plus 1, so it is now equivalent to 100. So we have 750 times 100 IB. Solving for IB, we have 4.8 minus 0.7 divided by 96 key plus 750 times your 99 plus 1, or that is equivalent to 100. So therefore, IB is equals to 23.97660.819 microampere. Then IC, which is equivalent to beta IB, so we have IC, that is 2.373684211 milliamp. And for your IE, which is beta plus 1 IB, so we have this IE. Then solving for the voltages, so we have your voltage at the base, which is equivalent to voltage base emitter plus 750 IE. So we have voltage at the emitter, remember that is 0.7. Then 750 times IE, we have already IE. So therefore, we have voltage at the base equals to 2.498245.098 volts. And voltage at your emitter, that is a voltage drop across 750. So that is 1.79824561 volts. Then at the output side, we have your collector voltage with respect to ground. And collector to emitter, we call that one as BCE. So applying KVL at the output side, so we have 12 minus 2.2 KIC minus voltage base emitter minus 750 IE. So therefore, we can solve for your BCE since IC and IE are already determined. So your BCE equivalent to 4.979649126 volts. And therefore, BC is equals to 6.7789473.6 volts. Then, we can solve also for the voltage from base to collector or base collector junction potential. So that is your base into collector. So solving for that, that is equivalent to your voltage base minus voltage at the collector. So we have a negative value because your voltage base is only 2.498245.614, whereas your BC or voltage at your collector is equivalent to 6.7789473.6 volts. So what is the implication of this value of your voltage base collector? So this is a reverse bias because we have a negative value for your voltage base collector. And remember that in active region, your voltage collector junction must be in reverse bias for linear amplification. Another bias is a voltage feedback bias. So we have a resistor connected at your collector going to the base. So we have your input side, and this is your output. During DC analysis, your capacitor are open. So we have your current, IC prime. Then at the collector terminal, it will split into IB and IC, and we have IE. If we have to get the current equation at your collector terminal, so we have IC prime minus IB plus IC. Then your current equation at your base, we have IE is equals to IB plus IC. So therefore, IC prime is equals to your IE. And remember your beta, the ratio, this is since it is a common emitter, the ratio will be your beta, which is equivalent to IC over IB. IC is beta IB, and IE is beta plus 1 IB. At the output side, by the way, we have to solve first the input side. So at the input side, first we have your voltage bit, base with respect to ground and voltage at the emitter with respect to ground. So applying KVL, remember that your IC prime is equals to IE, so therefore we have BCC minus RC IE. So this is now IE because IC prime is equals to IE. Then minus RBIB minus voltage base emitter minus REIE. And we have to express IE in terms of IB, which is beta plus 1 IB. Substituting that equation of your IE to your equation of your BCC, so therefore we have your BCC minus RB IB minus voltage base emitter minus your RC plus RE in quantity times quantity beta plus 1 IB equals to 0. Remember, RC has a current flowing IE and RE has also a current IE. So therefore, IB is equals to BCC minus voltage base emitter over RB plus quantity RC plus RE times the quantity beta plus 1. And IC is beta IB. And if we have to solve for the voltage at the base, that is voltage base emitter plus REIE. And for your voltage at your emitter, it is equivalent to the voltage drop across RE. Then at the output side, that is our BC with respect to ground, and between collector to emitter is your BCE. Applying KVL, so we have BCC minus RC, IC prime minus BCE minus RE, IE equals to 0. And we know already that IC prime equals to IE. Then both IE and IC are known already, but this equation we have only IE, so therefore we can solve for your BCE. And also, solving for your BC, that is equivalent to your BCE plus BE, or voltage at your emitter. So for example, we have this circuit, you have to determine as well as your BC. So during this analysis, you have your current. It is IC prime, that is from BCC going to your collector terminal. At the collector terminal, it will split into two. Your current become IB and IC, and at the emitter, it is IE. So we have your voltage at the base with respect to ground and voltage at your emitter with respect to ground. So at the input analysis, you have 12 volts minus 2.2 k IC prime minus 220 k IB minus voltage base emitter minus 750 I equals to 0. Remember that IC prime equals to IB IC and IE equals to IB plus IC, so therefore IC prime equals to IE, and IE is beta plus 1 IB. So therefore, solving for your IB, we have 12 minus 0.7, that is your voltage base emitter, all over 220K plus quantity 2.2K plus 750 times 99 plus 1. So we have this IB, solving for your IC, and this is our IC, and solving for your IE, this is also our IE. So at the output side, we have your BC at the collector terminal and your collector emitter voltage or BCE. So applying KVL at your output side, we have 12 minus 2.2 k IC prime minus BCE minus 750 IA. Since IC prime equals to IE and IE have known already, so therefore we can solve for your BCE. So this is our BCE. Then for BC, that is equivalent to your BCE plus your voltage drop across 750. So this is your BC. And for your BE, that is a voltage drop across 750, then this is your BE. and the voltage at the base, that is equivalent to your voltage base emitter plus your voltage at your emitter. So we have this voltage at the base. And your voltage base collector, so we have your voltage at the base minus your voltage of your collector. So we have a negative value for your voltage base collector because it is in active region of operation. So it needs reverse bias for your voltage base collector. Another configuration is a common collector, and it is also called emitter feedback bias. So this is your common collector. Your input now is at base, but your output is at the emitter. So input is at the base, output is at the emitter. And during DC analysis, all of these capacitors are open. So we have the same circuit with your emitter bias. So solving for your TCL, for your current, we have IE equals to IB plus IC, and the ratio or DC ratio for your common collector is the same DC ratio of your common emitter. So we are using beta, that is IC over IB. So IC is equals to beta IB, and IE is equals to beta plus 1 IB. So at the input side, you have your voltage base and voltage at the emitter. So you're applying KVL, we have VCC minus RBIB minus voltage base emitter minus RAIE equals to 0. Since IE is beta plus 1 IB, so therefore we can solve your IB as VCC minus voltage base emitter over RB plus RE times beta plus 1. And IC is beta IB. Solving for your voltage at the base, that is voltage base emitter plus the voltage drop across RE. And RE is equals to, or voltage at the emitter is equals to RE times IE. So at the output side, that is our BC, collector to emitter voltage, applying your KVL, so we have BCC minus RCIC minus BCE minus REIE. We know already IC and IE, so therefore we can solve for your BCE. And your BC is equals to your BCE plus your voltage at your emitter. So we have this example. So we have to solve all the current, IB, IC, all the voltages, VB, or voltage at the base, voltage at the emitter, voltage at the collector, as well as your voltage base collector junction. So during DC analysis, we have this circuit, we have that current, we have IB and IC going to your transistor, and IE is going out from your transistor. So this is our voltage at the base, voltage at your collector, and voltage at your emitter. Between your collector and emitter, we call that one as BCE. So at the input side, we have this equation, 12 minus 240 KIB minus voltage base emitter minus 750 IE. And if we have to express IE in terms of IB, so that is beta plus 1 IB. And our beta is equivalent to 99. So therefore, IB is equals to 12 minus 0.7 over 240 kilo ohms plus 750 times your beta plus 1, which is 99 plus 1. So therefore, IB is equals to this value. Solving for your IE, which is beta plus 1 IB, so this is our IE. And solving for your IC, it is beta IB, and this is IC. Then at the output side, applying KVL, so we have 12 minus 2.2 key IC minus voltage collector emitter, then minus 750 IE. So IC is equivalent to 3.551428571 milliamp, and IE is equivalent to 3.587301587 milliamp. So therefore, we can solve for your BCE. So BCE is equals to 1.496380954 volts. And for your BC, that is equivalent to your BCE plus the voltage drop across 750. So that is our BC. If we have to solve for the voltage at the base, that is voltage base emitter plus your voltage drop across 750. So that is our voltage at the base. Then for your voltage at your emitter, that is a voltage drop across 750. And if you have to solve for the base collector junction voltage, we have voltage base minus voltage at your collector. So we have a negative value. Since in a linear operation or active operation of your amplifier, your collector or base collector junction must be in reverse bias. Then we have the common base configuration. So this is our common base configuration. We have your input now at your emitter, your output at the collector. So during DC analysis, capacitor are open. Then we have a current going to your transistor as IE, and going out from the transistor is IB and IC. The transistor that we are using at this type of configuration is a it is a PNP. So we can also use an NPN for this type of configuration. So we have to solve for your current using KCL. So we have IE is equals to IB plus IC, and the DC ratio of this common base is what we call the alpha. So alpha is equals to output over input, so we have IC over IE. So therefore, IC is equals to alpha IE. And if we have to substitute your IC to your equation of your IE, so therefore we have IE equals to IB plus alpha IE, and solving for your IB is equals to 1 minus alpha IE. If we have to get the relationship between your beta and alpha, so remember that the equation of your IE is equals to IC plus IB in any configuration. Either it is a common emitter, common base, or common collector. We have the same flow of your current, which is IE is equals to IB plus IC. So for beta, we have IC over IE. And we can express our IB as IC over beta. And for alpha, we have IC over IE. And we can express IE as equivalent to IC over alpha. Substituting this value to your equation of your emitter current, so we have IC over alpha is equals to IC over beta plus IC. And if we have to divide this equation by IC, so therefore we have 1 over alpha equals to 1 over beta plus 1. Solving for your alpha, so we have to get the least common denominator of your right side, so that is equivalent to 1 plus beta over beta. So therefore alpha is equals to beta over beta plus 1. And if we have to solve for your alpha in terms of beta, so therefore we have to transpose your 1 to your left side and get the LCD of your left side. So we have 1 minus alpha over alpha equals to IB, or I over beta. So therefore beta is equals to alpha all over 1 minus alpha. So at the input side, applying KVL, we have BEE minus REIE minus voltage base emitter minus RBIB. Since IB is equals to 1 minus alpha IE, we have to substitute that to your equation. So therefore, your equation is equals now to BEE minus REIE minus voltage base emitter minus RB times quantity 1 minus alpha times I equals to 0. So therefore, we can solve for your IE, which is equivalent to your BEE minus voltage base emitter all over RE plus RB times 1 minus alpha. And IC is B alpha IE. Solving for your voltage at the emitter, so we have voltage EE minus REIE or voltage base emitter plus the voltage drop across RB. Solving for your voltage at the base, so we have voltage drop across RB. So we have RB times IB. At the output side, so we have your voltage base collector. So we have RB times IB minus voltage base collector minus RC IC equals to 0. So why your RB IB is positive? Remember that a current will enter at your resistor as positive, then it will go as a negative. So if we have to get the loop from this side, so therefore we have positive RBIB minus voltage base collector minus RC IC equals to 0. So solving for your voltage base collector, that is equals to RBIB, since we have already IB as well as ICs. So we have RBIB minus RCIC. So BC is equals to RCIC. And for that example, we have this one. We have to solve for the current as well as the voltages. So during BC analysis, so we have your voltage at the emitter from emitter terminal with respect to ground, voltage at the base, that is the voltage step across 80K, voltage at your collector, that is a voltage across 4K or from collector terminal going to the ground. And we have the voltage BC. Input side, applying KVL, so we have 12 minus 1.2K IE minus voltage base emitter minus 80K IB. We have to express your IB in terms of IE, so we have 1 minus alpha IE. Substituting that one to your IB at your input side equation and solving for your IE, so therefore IE equals to 12 minus 0.7 all over 1.2K plus 80K times 1 minus 0.97. So therefore, this is our IE. And your IB, which is 1 minus alpha, so we have this IE in microampere or 94.16667 microamp. And IC is alpha IE, so IC is equals to 3.044722 milliamp. At the output side, so if we have to solve for your voltage at the base, so that is a voltage drop across 80K times your IB. So we have 7.5333 volts. Then for your voltage at your emitter, that is equivalent to your voltage base emitter plus the voltage drop across 80K, or that is 80K times IB. So this is our voltage at the emitter, which is 8.2333 volts. And the voltage across your collector, or voltage at the collector, which is equivalent to the voltage drop across 4K. So we have 12.17888 volts. Now we can solve for your voltage base collector. That is voltage base minus collector voltage. So that is equivalent to negative 4.64555 volts. To satisfy that your voltage collector junction must be in reverse bias if your amplifier is in active region. Next, we have this multi-stage connection. For most systems, a single transistor amplifier does not provide sufficient gain. So gain, we can solve gain at your easy analysis, or will not have a correct input and output impedance matching. The solution is to combine multiple stages of amplification. So we have this one. We have your input. It is connected to the first amplifier. The output of your first amplifier will be connected to the input of the second amplifier. Then the second amplifier output to the first amplifier, and so on. So if we have an amplifier, so if we have to get the gain, if we are using the gain, voltage gain, so we have a total voltage gain. We call that one as EB total. It's equivalent to the gain of your first amplifier times the gain of the second, the third, and so on. So we can have this gain equation or discussing this gain when we reach your easy analysis, as well as your impedance matching. Impedance can be solved at the easy analysis. So we have different types of multi-stage connection. We have the cascade, and the Darlington pair. So what is a cascade connection? Cascade connection, the output of the first stage is coupled to the input of the next stage using a coupling device. This device usually a capacitor or a transformer. So we use to create amplifiers. So the purpose of this is to use to create amplifiers with high input impedance, low output resistance, and a large gain. The purpose of coupling device is to transfer the EC from the output of one stage to the next stage. So that is through the input of the next stage. And to block the DC to pass from the output of one stage to the input of next stage, which means we have to isolate the DC condition. Then we have different types of cascade connection. We have the RC coupling, the direct coupling, and the transformer coupling. But we are only discussing in your DC analysis the RC coupling and direct coupling. So we have first the RC coupling circuit. So we have your stage 1 and stage 2. Between your stage 1 and stage 2, it is connected with a capacitor. So your coupling device is the capacitor. Then, during DC analysis, capacitor are open. So we have now this circuit. So stage 1 is independent with your stage 2. So we can solve individually your stages. So for stage 1, that is a voltage divider bias. So since it is a voltage divider bias, so we have to use your Thevenin's theorem. So we have first to get your VTH as well as your RTH. And then we have to redraw your Thevenin's equivalent circuit. It is this one. And applying your KVL at the loop of your transistor at the input side. So we have VTH minus RTH IB1 minus voltage base emitter 1 minus RE1 IE1 equals to 0. And we have to express IE in terms of IB. So therefore, IE1 is equals to beta 1 plus 1 times IB1. Substituting that 1 to your equation of your VTH and solving for your IB. So we have IB1 is equals to VTH minus voltage base emitter 1 all over RTH plus RE1 times beta 1 plus 1. For IC1, that is beta 1 IB1, and for the voltage from your base with respect to your emitter, that is voltage base emitter plus the voltage drop across RE1. And for the voltage at your emitter, that is the voltage drop across RE1 or RE1 times IE1. At the output side of your Stage 1, you have your BCC minus RC1, IC1 minus BCE minus RE1, IE1 equals to 0. So we can solve for your BCE 1, that is collector emitter junction. So equals to BCC minus RC1, IC1 minus RE1, IE1. And if we have to solve for your collector voltage with respect to ground, or that is BC1, so that is BCE1 plus RE1, IE1. Then at stage 2, we have the same configuration or biasing, which is a voltage divider bias. So we have first to solve for your VTH as well as your RTH. And we have to redraw the circuits of your Thevenin's equivalent circuits, and using your KVL, and we have to express IE in terms of IB. So IE2 is equals to beta 2 plus 1 times IB2. So therefore BTH is equals, or BTH minus RTH IB2 minus voltage base emitter 2 minus RE2 times beta 2 plus 1 IB2. So therefore we can solve for your IB2, which is BTH minus voltage base emitter all over RTH plus RE2 times beta 2 plus 1. So IC2 is beta 2 IB2. And voltage base 2 is equals to voltage base emitter 2 plus RE2 IE2. And for the voltage at your emitter is a voltage drop across RE2. Then for stage 2, output side, so we have your BCC minus RC2 IC2 minus BCE2 minus RE2 IE2 equals to 0. So solving for your BC2, since we have already the value of your IC2 as well as your IE2, so that is equivalent to your BCC minus the voltage drop across RC2 minus the voltage drop across RE2. And if you have to solve for your BC2, so that is BCE2 plus the voltage drop across RE2. For the direct coupling bias, we have this circuit, stage 1 and stage 2. Between stage 1 and stage 2, it is directly connected from the output of your stage 1, it is connected directly to the input of your stage 2. So during DC analysis, so we have this one, you have IB1 going to your transistor, and then we have your IE, and it will split to this terminal into IB2 and IC1. Then we have your IE1 and we have IC2 and IE2. So at the input side, using KVL, we have BCC minus RB times IB1 minus voltage base emitter 1 minus RE1 times IE1 equals to 0. And we have to express your IE in terms of IB, so we have IE1 equals to beta 1 plus 1 IB1. Substituting that one to your equation, then we have BCC minus RB times IB1 minus voltage base emitter 1 minus RE1 times beta 1 plus 1 IB1 equals to 0. So therefore, we can solve for your IB1. It is BCC minus voltage base emitter 1 all over RB plus RE1 times beta 1 plus 1. And IC1 is equals to beta 1 IB1. Then if we have to solve for the voltage base 1, that is from base of your transistor 1 with respect to ground. So that is voltage base emitter 1 plus the voltage drop across RE1. And if we have to solve for the voltage emitter 1, so that is a voltage drop across RE1. Then stage 1 output side, applying your KVL, So we have BCC minus RC1 times I minus BCE1 minus RE1 IE1 equals to 0. Your I is equals to IC1 plus IB2. We know already the value of your IC1, so we don't know the value of IB2. So we have to substitute that one to your I in your RC1. So we can solve for your BCE1 equals to BCC minus RC1 times IC1 plus IB2 minus RE1 IE1. Since we don't know the value of your IB1, so we have to go to your stage 2. So first, the equation of your BCE1 is equals to BCE1 plus RE1 IE1. So at the input of your stage 2, we have BCC minus RC1I minus voltage base emitter 2 minus RE2 IE2 equals to 0. Remember, I equals to IC1 plus IB2. You have to substitute that one to your I, and we know already the value of your IC1, so we have to determine what is the value of your IB2 and IE2. But we have to express IE2 in terms of IB2. So we have beta 2 plus 1 IB2. Substituting that to your equation, so we have this equation. Now we can solve for your IB2. Remember, IC1 have already a value in the previous slide. So IB2 is equals to BCC minus voltage base emitter 2 minus RC1 IC1 all over RC1 plus RE2 times beta 2 plus 1. And IE2 is beta 2 plus 1 IB2. IC2 is equals to beta 2 IB2. If we have to solve for the voltage at the base 2, that is equals to voltage base emitter 2 plus RE2 IE2. And for the voltage at emitter 2, it is equals to a voltage drop across RE2. Stage 2 output side, so we have BCC RC2 IC2 minus BCE2 minus RE2 IE2 equals to 0. Since the current value have already been solved, IC2 as well as IE2, therefore we can solve for your BCE2. BCE2 is equals to BCC minus RC2 IC2 minus RE1 IE1. Oh, that is RE2. So this is RE2, RE2. And for your BC2, so that is BCE2 plus RE2 IE2. For the cascade connection, it is a two-stage amplifier of a single transconductance amplifier, usually a common emitter stage followed by a current follower stage, usually a common base. So for this cascade connection, it is for high input-output isolation and have a higher input impedance, higher output impedance, higher gain and lower bandwidth, or lower gain and higher bandwidth. So this is the connection, what we call the cascade. We have stage 1, which is common emitter, and stage 2, a common base. So during DC analysis, all capacitors are open. So we have your current IB going to your transistor 1. We have this one as current I. Then it's split into two. We have IE2 and IC1. This is your IE1. And we have your IB2 and IC2. So first, we have to solve at your stage 1. So at the input of your stage 1, applying KVL, so we have BCC minus RB1 IB1 minus voltage base emitter 1 minus RE1 IE1 equals to 0. And we have to express IE1 in terms of IB1, so that is beta 1 plus 1 IB1. So since if it is a common base, the ratio will be alpha, so we have just to call your ratio in your transistor 1 as beta. So therefore, IB1 is equals to BCC minus voltage base emitter 1 all over RB1 plus RE1 times beta plus 1. And IC1 is equals to beta IB1, and the voltage base 1 is equals to voltage base emitter 1 plus RE1 IE1. And for the voltage at your emitter 1 is equals to the voltage of across RE1. At the output side of your stage 1, we have BCC minus RC1I minus BCE1 minus RE1 IE1. So remember, I is equals to IC1 plus IE2. Since we have already the value of IC1, we have a variable IE2, or we don't have any value for your IE2. So we can substitute that I to your equation, then solving for your BCE1. But first, we have to solve your IE2. If you have to solve for your BC1, so this is in terms of your IE1 and BCE1. At stage 2, we have BCC RC1 or BCC minus RC1 I times I minus voltage base emitter 2 minus RB2 IB2 equals to 0. So remember that your I is equals to IC1 plus IE2. Substituting that one to your equation BCC minus RC1I. So we have this equation, and we have already the equation of your IC1. So therefore, we have to solve for your IE2. But we have to express IB2 in terms of IE2, which is 1 minus alpha IE2. So we have IE2, solving for IE2, we have BCC minus voltage base 2 minus RC1 IC1 with no already IC1 from the previous slide, all over RC1 plus RE2 times 1 minus alpha. Then IB2 is 1 minus alpha IE2, and IC2 is alpha IE2. Solving for your voltage emitter 2, that is voltage base emitter 2 plus the voltage drop across R2 or RB2. Then voltage base 2 is equals to the voltage drop across RB2. And BC2, that is a voltage drop across RC2. Next is a Darlington pair connection. It is named after Sidney Darlington. It is a special arrangement of two standard transistors connected together. The emitter of one transistor is connected to the base of the other to produce a more sensitive transistor with a much larger current gain, useful in amplifications where current amplification or switching is required. So this is the circuit of your Darlington pair. We have an emitter of your first stage connected to the base of your second stage, and you have the same collector connection. And during this analysis, capacitor are open. So we have IB1, then we have your I, it will split into two. We have IC1 and IC2. Then your IB1 is the same as your IB2, and we have your IE2. So at the input side, we have to get the equation using your KBL. So we have BCC minus RB IB1 minus voltage base emitter 1 minus voltage base emitter 2, then minus RE IE2 equals to 0. If we have to express IE2 in terms of IB2, so that is beta 2 plus 1 IB2. So the equation will be now equivalent to BCC minus RB, IB1, minus voltage base emitter 1 minus voltage base emitter 2 minus RE times beta 2 plus 1 IB2. But IB2 is equals to IE1. So this is now our equation if we have to substitute IB2 as IE1. And we have to express IE1 in terms of IB1. So we have IE1 equals to beta 1 plus 1 IB1. So therefore, your equation will be BCC minus RB IB1 minus voltage base emitter 1 minus voltage base emitter 2 minus RE times quantity beta 2 plus 1 times quantity beta 1 plus 1 IB1. So therefore, we can solve for your IB1. So that is BCC minus voltage base emitter 1 minus voltage base emitter 2 all over RB plus RE times the quantity beta 2 plus 1 times quantity beta 1 plus 1. Then for your IE1, that is beta 1 plus 1 IB1. And since IB2 is equals to IE1, therefore IE2 is equals to beta 2 plus 1 IB2. IC1 is beta 1 IB1. IC2 is beta 2 IB2. So solving for the voltage at the base 1, so we have voltage base emitter 1 plus voltage base emitter 2 plus the voltage drop across RE. And if we have to solve for the voltage emitter 1, which is also a voltage base 2, so we have voltage base emitter 2 plus the voltage drop across RE. And RE is RE times IE2. Then for your voltage at your collector 1, which is also the same as your voltage at your collector 2. So that is equivalent to BCC minus RC times I. Remember, I is equals to IC1 plus IC2. Then BCE1 now is equals to your BCE1 minus voltage base 2, or that is equivalent to your voltage emitter 1. For BC2, that is equivalent to your BCE1 minus your voltage emitter 2. So that is for your DC biasing circuit. So a maximum transistor ratings, it is like any other electronic devices. A BGT has also limitation on its operation. These limitations are stated in the form of maximum ratings and are normally specified on the manufacturer's datasheet. The typical ratings are the following. We have the collector to base voltage, collector to emitter voltage, emitter to base voltage, collector current, and the power dissipation. So for power dissipation, if we have to solve for power, that is equivalent to collector times collector. That is voltage times your current. So for the maximum transistor rating, we have this one. Your BCE and IC must not exceed the maximum power dissipation of PD. Remember that power or PD is equal to BCE times IC. If BCE is at maximum, then we can solve IC as PD maximum over BCE. And if IC is at maximum, so we can solve BCE, that is PD maximum over IC. So the first one, BCE is maximum, so they have PD maximum over BCE, that is how to solve for your IC. And the other one, if IC is a maximum, then we have PD maximum over IC, it is how to solve your BCE. So we have this example. A certain transistor is to be operated with BCE equivalent to 6 volt. If its maximum power rating is 250 milliwatts, what is the most collector current that it can handle? So we have IC equals to PD max over BCE. So therefore, IC value or the current at your collector must be equivalent to 41.6666 milliampere. So this is the maximum or most collector current that your transistor can handle. Another example, the transistor in the circuit below has the following maximum rating. The PD maximum is 500 milliwatts, the BCE maximum is 15 volts, and the IC maximum is 100 milliampere. So we have to determine the maximum value to which BCC can be adjusted without exceeding the given rating. So we have this circuit. So we have the current flowing in the circuits. We have IC going to your transistor as well as IB. Then we have IE going out from your transistor. So at the input side, since BCC is unknown, so first we have to solve for your IB. So at the input side, using KVL, so that is 8 volts minus 40 KIB minus voltage base emitter minus 750 IE. We have to express IE in terms of IB. Given beta is 99, so therefore IB is equals to 8 minus 0.7 all over 40K plus 750 times beta plus 1. So 99 plus 1. So we have now IB equivalent to 63.47826087 microampere. And your IC is equals to beta IB. So we have 6.284347826 milliampere. And IE is equals to 6.347826087 milliampere. Solving for the voltage drop across RC. So we have already IC. So voltage across RC, that is 22K times IC. So we have 13.82556522 volts. Solving for the voltage drop across RE, since we have already IE, then we can solve for your VRE. So that is 750 IE. So we have 4.760869565 volts. So we are now going to solve for the maximum value of your BCC. So that is BRC plus your BCE plus your BRE. So we have already a BRC value. Then in the problem, your BCE maximum is also given, and we have already solved for your voltage drop across RE. So therefore, the maximum value for your BCC will be equivalent to 33.58643479 volts. So that is the maximum adjusted value for your BCC. So we have to determine if your PD maximum exceeded the maximum value. So first we have to solve for PD, it is BC max times IC. So your PD is only 94.2652179 millivolts. So this PD did not exceed to your PD maximum, it is 500 milliwatts. And that's all for our DC biasing of our bipolar junction transistor.